All right, thanks everybody for joining us for another DoKC Town Hall. I'm Paul, head of community for Data on Kubernetes Community. Today we have a really awesome talk with Sri Yayi and Vigith Maurice from Intuit. Today's talk is empowering developers with easy scalable stream processing on Kubernetes. Before I hand things over to them to give their presentation, I will of course go over all the community announcements that we have. Yeah, so first of all, I wanted to thank our community sponsors. So our gold sponsors are Google Cloud and Percona. And then we also have our silver sponsors and our community collaborators. And we actually have a new community collaborator, which I'll talk about shortly. But thank you to all of our sponsors for helping us, which allow us to put on these live streams, to do other sort of events and help run the community. So thanks a lot. So yeah, as I mentioned, we actually have a new community collaborator. So if you remember last week we had Deepti Sigaretti, who's the maintainer and project lead for Vitess. So Vitess has joined Rook and Apache Unicorn as our newest Data on Kubernetes community collaborator. And the point of that program is just to bring in open source projects in the DoK sort of space to help foster collaboration in the community. So yeah, welcome Vitess to the community collaborator program. Also, just a quick reminder, if you're heading to KubeCon, the schedule is out for DoK Day, which is on November 12th. Make sure you get the all access pass if you want to attend. The passes are the all access passes won't go up until November 9th, so you have a bit of time to buy a pass if you're going. But yeah, I also want to give a thanks to Percona again as being the gold sponsor of the event. So it's really important that we have the sponsorship for the event, which allows us to keep being brought back as a co-located event at KubeCon. So KubeCon is KubeCon North America hasn't happened yet, but KubeCon EU 2025 is in London on April 1st through the 4th. The CFP for KubeCon is open until Sunday, November 24th at 11:59 GMT Standard Time. So yeah, get those proposals in. This is for KubeCon, the greater event. You scan the QR code, that will get you a link to the CFP page, and you can learn how to submit your proposals. Some upcoming events for us for Data on Kubernetes. Next week, we'll have Victor Gamov, who will be talking about scaling real-time analytics and Apache Pinot on Kubernetes. And then our town hall next month, we're going to have Michael Levan, who will be talking about AI and ML on Kubernetes for the absolute beginner. So don't miss out on that. Also, we have Nelson Crapaldi, who will be talking about his new book, Big Data on Kubernetes. If you scan the QR code on the right, that'll take you to our meetup page. Hopefully, I guess if you're here today, you probably already know about our meetups, but you can register for our meetup group and for the individual events. So check that out. And of course, if you want to get involved in the community, scan the QR code on the left. That'll take you to the community page. It'll tell you how to get involved, give you links to all the channels that you can work in. And then also, if you're interested in becoming a sponsor of the community, scan the QR code on the right. That will give you some information there. So that is it for me. I just want to say before I hand things over, if you have questions for Vigith and Sri, just put them in the chat and we'll pass them along to them. Most likely we'll get those questions answered at the end. But yeah, I will now hand things over to Sri and Vigith.
Awesome. Thanks, Paul. Thanks for this great community for giving us the opportunity to share about our open source project and how we are doing scalable stream processing it into it. Let me share my screen quickly. I think you can see my screen, right?
Yeah, I can see it.
Perfect. Awesome. Hi, everyone. I'm Sri. I'm a product manager on the Intuit developer platform team. And today I have Vigith, who is also along with me. We are going to share about how we are empowering our developers to do scalable stream processing on Kubernetes using an open source project called as Numaflow. So on a very high level, here is our high level agenda for our conversation, where we'll just quickly introduce about like what do we do at Intuit as a platform team, discuss a little bit about the stream processing, what are the challenges that developers or anyone are facing as of today, and how did we solve them using Numaflow, and then do a demo and how community is also using the open source project. So we'll share about all of the various good and the greatest use cases. So, as majority of you might be already aware, Intuit is a global fintech platform company with product offerings like TurboTax, QuickBooks, Mailchimp, and Credit Karma. And if you look at some of the numbers down there, like we are a completely modern SaaS platform that's run on Kubernetes. All of our services are on Kubernetes, and you can see at the scale that we operate, either in terms of machine learning and the amount of money that we process on a yearly basis, and the number of connectors that we have with like various financial institutions across the board. And we are a big believer in open source. If you are in the Kubernetes ecosystem, majority of you might be already aware of like the Argo project, which was actually incubated at Intuit and then open sourced to the broader ecosystem. And some of our learnings from Argo workflows and all of that has helped us to start on this new journey of another project called as Numaflow. Some of the use cases that we have learned and how did we go about solving them is what we are going to share as we go along during this presentation. With that, let's dive deeper into the today's topic, which is basically the stream processing. What do I mean by stream processing, right? Like essentially, you as a developer or as a data engineer or as an ML engineer, what you try to do is like you try to act upon the events that as they come in. It could be for different kinds of use cases. Either it could be like real-time analytics that you would want to do, or some kind of event-driven applications that you would want to develop, or do some kind of predictions or inference on the data that is coming in real time. So you're trying to act on these events as they are coming in. And today, probably we are going to focus more around like stream processing, which is like a real time, as and when the events come in, you just act upon them. So that's like a quick introduction of stream processing, where you have a stream of inputs that you're receiving, you are doing processing on that data, and then you're sending this data to like process data into downstream. It could be like databases for analytics reasons, or for dashboards, or it could be n number of use cases. And that's like a very high level introduction of stream processing, but we can always spend a lot of time in like unpacking what entails into stream processing, what are the challenges and all of that. So we are going to cover some of those. Now, let's take some of these examples like that we see on a day-to-day basis, right? For example, if you are in the e-commerce ecosystem, you would want to process and understand how many orders were uh, done on real time. Let's say in the past 1 minute, how many orders were placed, or probably you want to send out recommendations to your users based upon the various actions that they are taking within the product. The other use case could be is like in industrial ecosystem, where you want to receive data from different kinds of IoT sensors, and then you want to process data and then take certain actions. Let's say probably preventive maintenance, or probably some kind of like shutdown protocols that you would want to execute. So that's like another set of use cases that you would see on a day-to-day basis. And the third one, which I've already mentioned, which is like the real-time analytics use cases. This can be like simple pricing related real-time insights. Let's say, for example, like how many orders have you placed through maybe Uber Eats or DoorDash or any of those, right? You would want to understand so that you can do dynamic pricing, you can do some kind of demand forecasting so that there are dashers available in order to deliver the orders and things like those. So that is like more of the real-time analytics use cases. And then lastly, of course, you can see a lot of fraud detection uses, especially in the fintech world that we operate in, right? Like when there's a kind of a transaction that is made, we want to make sure that it's a valid transaction, it's not a fraudulent one, and all of that. So all of these are like need to be done real time, such that there is no impact to the customers that who are actually using our products in as such. So in short, you can see like diverse set of use cases, right from like e-commerce to fintech to like the IoT, or in general like the real-time analytics use cases. Like the real-time stream processing use cases you generally come across the board, and they are kind of the backbone of our existing ecosystem, or the modern products that we are trying to develop. So let's try to take a look at like how does the architecture look like when you are trying to build these stream processing systems, right? So we have discussed about different use cases like either e-commerce or like financial or IoT and all of that. So all of these events that you receive, it could be purchasing orders or payment orders or maybe IoT sensor data. It can come through different kinds of sources. It could be right from like your Kafka, most often than not, Pulsar, SQS, SNS, and like different kinds of message streaming or event streaming buses is what generally people tend to use as sources in order to receive your events. And once you receive these events, you want to act on them, right? Like the kind of processing could be either you act on each of those events, or probably do you want to do some kind of aggregation, and it can be n number of things, right? Right from just simple processing to doing some kind of prediction, aggregations, and like whatnot. And once you process this data, of course, you would want to send this to your downstream. It could be any other, again, like the way we have discussed it, the syncs can be either like a databases or again your event streaming systems or any of those. So in short, if you look at it, you need some sources where you are receiving the data, and the second is like you're trying to process the data, and then you're sending this data, whatever you have processed, into your downstream system, so that your probably other systems can consume and then act upon those events as well. But let's try to understand like what are the challenges that we started seeing when specifically at Intuit, or even in generally across the broader ecosystem on with respect to stream processing, right? So the first and foremost is real-time event processing is a big it's kind of a challenging thing, especially for folks who are not in the world of data engineering. Let's say you are a data engineer and you might be writing tons of event processing or real-time stream processing jobs on a day-to-day basis. But if you try to unpack the existing ecosystem, it's kind of heavy on Java frameworks, and also you need to learn about the concepts of the stream processing or the real-time stream processing. So that is like one of the biggest pain points. Let's say you are an ML engineer or probably an application developer, but you have a use case of trying to do some kind of real-time event processing or the stream processing. You would have to move out of your existing ecosystem. Let's say you are a Python or probably a Go developer. You have to move out of your existing comfort zone and learn a new platform altogether in order to build these jobs. And that is like one of the most common pain point that we have heard from our internal developers and everyone. The second is like complex integration. Like in your the previous architecture diagram that you have seen, right? Like you have a lot of event sources, right? From like Kafka to Pulsar to SQS and all of these. It's not just about connecting to multiple event sources. You would also have to think about the operations and maintenance and anytime any changes that happen. So connecting to multiple sources and syncs is not something that the every a developer or ML engineer or a data engineer are super excited about, and they'll have to write a lot of boilerplate code to start with. So that is like another pain point. And then lastly, there are scaling complexities. When we think about scaling complexities, like the first thing that I want to iterate upon is that at Intuit, we are completely a Kubernetes ecosystem. But when you think of like Kubernetes, it's more in the context of like a microservices, a single entity that will serve like HTTP requests and all of that. But they may not Kubernetes as such is not uh, kind of more focused on the data movement and the data processing kind of like the ecosystem. So there are different kinds of scaling challenges from a platform team perspective that you would end up with. Like first, in simple terms, like let's say if you think about auto scaling in the Kubernetes ecosystem, ideally you would use your HPA, which is reliant on the let's for example, like resource utilization, memory utilization, like CPU and whatnot. But ideally, when you think about your event processing systems, you would want to think about factors like, hey, how many events am I receiving from my upstream event sources? Like, at what rate am I processing? And once I write these events to your downstream, probably to a DB or whatever it may be, you cannot scale to beyond a particular point. So you'd have to consider like multiple factors even before you scale your event consumers. So in short, like combining all of these different kinds of pain points from like developers, like the ML engineers, or even the data engineers, where they're struggling to uh, understand the complex data engineering frameworks, and then unable to move away from their existing languages or the comfort that they are more used to, and then operations that you'd have to take care of in terms of scaling, and all of these made us to think about and then build this new project called as the Numaflow. I'll hand it over to Vigith. He's right next to me, and then he'll share a lot more about the Numaflow platform. What does it entail, and how can you go about writing piece of stream processing jobs? And we'll also share some demo after like Vigith kind of introduces the Numaflow as a platform. With that, over to you, Vigith.
Thank you, Sri. So let me get in weeds with what Numaflow is about. So when we designed Numaflow as an open source solution, right, what we did was we wanted to design as a serverless platform. This is because um, uh, developers tend to like when it is managed for them, and that improves their productivity, so they can focus on what they love doing the best, that is writing business logic or the code that really matters. For ML engineers, that is machine learning, things like that. Right. So first and foremost, what we had to do is we had to abstract the infrastructure. That means users do not even have to talk about what is the auto scaling needs they have, right? We wrote controllers so that to extend Kubernetes to understand streaming philosophies onto it, right? It's no longer a simple health check on an endpoint, but rather understand back pressures and scale accordingly. Second is that as things evolve, we use multiple data, unbounded streams. For example, at Intuit, we use Apache Pulsar. Kafka is one of the major backbone on eventing. We also use things like SQS, that is Amazon's Q, and so forth. So we wanted also the users not to worry too much about where the data is coming from, because they really don't care where it is coming from. Rather, they're interested in the data in the payload. Right. So we thought, okay, we have to decouple it. So they just focus. This means that when you write the code and deploy, let's say, quote unquote, like in Lambda, Amazon Lambda, right? You just write the code and say, okay, invoke this piece of code either through API gateway calls or some SNS calls. And lastly, we wanted to make it scalable and reliable, because these are running on containers that depends on other systems, right? So we wanted to make sure that we should be able to do quick deployments with zero downtime, and zero-day vulnerability should be patched as soon as possible, right? For this, Numaflow actually comes with its own control plane called NumaPlane, and that's how we do it. But this is the key thing. From a user perspective, this is given out for them. They don't have to worry about any of the things like infrastructure, sources, nor about the security and the scalability aspect. With that, let me just walk you through what an event processing graph looks like. So it all starts with an unbounded source. This could be Kafka, Apache Pulsar, you name it. It can be anything. You can write on your own source. It does much more than just from the underlying Numaflow does much more than that. It tracks event times and watermarks and so forth for completeness properties. But it all starts with a stream. And then once the data is read in, it's passed over to the user, right? User container or user-defined function. What it does is the user has to do is they need to read the message given to them that is given out for them, and they can make one, zero, one, or many. Basically, filter the data out if it is not valid. Let's say formatted correctly. One meaning is the 1:1 translation. I mean, for every input you want to write out a sentiment analytics, for example, right? Or there could be zero to many. That those are like enrichment use cases or right amplification use cases. Once you have processed the message, you can make a decision, a runtime decision, to say where to send this message. Should it go the path A or via path B or both paths? There could be many paths it could choose. These are very powerful in A/B testing in ML, and also choosing which kind of ML model, for example, to choose. Cases where we have low density data, you want to use a sparsity model, versus in some cases you want to run a model that is placed on GPU. What it means is all these circles you see in the graph can be independently placed in different node types. For example, one UDF could be running in GPU, right? So those powerful features help users to choose at runtime what path the message should take. And lastly, it all ends up in a sync. Sync is a terminal stage where either you write back to a stream or you persist into your database. It shouldn't matter. And Numaflow's guarantee is from the source to sync. So any data that comes in the source is reliably forwarded all the way in an exactly once formatting semantics all the way to sync. No data will ever be lost or corrupted. That's the guarantee we provide to the developers. Now that you've seen the graph, let me walk you through how does it take to write a serverless eventing function. So this is a Python example I noted via the symbol down there on the top, bottom right. Um, so if you look at the signature, we give them a datum. Datum is a type, is an interface, and all the function need to do is respond, give back the messages. It does not talk about Kafka or anything. It's just about you are given a message, and this is the function we'll execute for every message that we get on the stream. Right. First and foremost, usually the design principle is you create the envelope to return the results because there could be 0, 1, or many. Right. So you create the envelope where you are going to push out the results. Then you do datum.value to get the data itself. What is the data? There are other things around, meaning you can get headers, get metadata like timestamp, so forth. But datum.getValue is where the real payload comes in. Then you can call your processing function. This could run for a while, right? In ML system, it could run for minutes. In some cases, it will be like symbol, millisecond, microsecond operations. Then you push the result to the list messages.append so that this message can be forwarded. Now you return the messages. In any part of this code, it doesn't talk about where the message is coming to or what to do if there is a transient network error. Platform takes care of everything. It guarantees you that for every message you receive, we will execute this function without fail. And no message, even if you, while after you return the messages, let's assume that there is a pod migration going on and the next vertex is maybe not running completely because of a cluster upgrade, we'll guarantee that this message goes through. Now, let me quickly show what I meant by dynamic routing, right? So this is the highlighted area where you can actually, when you append the message, right, you can annotate saying that tagged as left, meaning take the left path, tag as right, meaning right path, message dot drop, meaning drop the message. And by default, it is forward or all path. With this symbol semantics of a UDF function, you can build complex trees. And for example, in this case, you have multiple sources where you are writing to a single sync after being processed by different UDFs. You could do joins in some cases. You could have a cycles if you need be for iterative programming. This is more like you enrich and then you keep enriching till the enrichment is good enough. And lastly, you can even broadcast changes to the system using something called a side input so that these are like, if you think about it, the source never dries up. It's an unbounded source. So these are like fire and forget pipeline. So there is we need to give users some way to propagate information to adapt it to itself to the new needs of the environment. Now, I talked about UDFs. Now, let me show how easy to write your own source. See, as a platform developer, we cannot write all the sources out there. There are many sources, right, and many needs. If you remember in earlier Sri's slide, it was showing a lot of sources out there, and each company has their own way of reading from, even from Kafka. There will be ALEs, that is application level encryptions and policies applied to Kafka topic. It's not free for all read because there are PII data and things like that. So we needed to give a way to abstract the source. And this is an example in Rust. This clearly says that we are multi-language agnostic to an extent, right? You can, whoever implements this interface, for example, you should be able to read, you should be able to act, tell us how much is pending. This is for auto-scaling in purposes. And lastly, how many partitions do you have? This is for some advanced semantics like watermark, completeness, and so forth. But whoever implements this source can be a source vertex. Same goes for the sync. It should be very easy to write syncs because we cannot implement all the syncs out there. Every morning when I wake up, I see a new database out there, right? So we need to be, the platform should be adaptable to let users write the sync the way we need. And at Intuit, actually, most of the users use custom syncs rather than inbuilt syncs because they have very custom requirements on how they write it and how the data validations happen, right? So this is this is a Java example, and you just need to extend the syncer interface, and you are given an iterator. Here, instead of one message at a time, we give iterator because in most things, it's better to write batches for better throughput. And all we need to do is iterator.next, and it will give the next element and just respond saying that, okay, either all are successful or few of them have failed. Anything that is failed, we will retry. That is the guarantee the platform provides. This is a very high level architecture. I wouldn't do justice by talking about it in a minute, but I'll give you a very rough idea. The theory behind this is that it's very difficult to get persistent systems in stateful systems in Kubernetes, right? Along with the streaming semantics. So the way you need to read this high-level architecture is first is there's a green line on the very top showing data movement. Data moves from left to right for 99%, except when there are cycles, but still it's more towards push towards right, left to right. There's a negative pressure that happens against the data movement. That's the back pressure. This helps us understand how to auto scale systems, right? And now if you come in the architecture diagram itself, it's a tight loop between read, write, and act, right? And we read from something from the source takes it, does some bookkeeping work, writes to the nest to a raft protocol so that the message is never lost. It goes through a three-way raft, and the next vertex picks it up the moment the write happens. Once the write is successful, we acknowledge back saying that, okay, this message has been processed, right? And this tight read, write, act is the one that moves data for the natural data movement forward. And lastly, I've put in a blue line to show the watermark. Watermark is a completeness property which we also provide to make sure that there is no data older than this data. This is very powerful when you're doing some reduce semantics, which will help users to know when to close a window when they're doing a 1-minute aggregation. This is a distributed system, and we need to make sure that there will be some slow vertices and slow ports. So we need to track the completeness property. Now that I've told this, let me summarize what Numaflow is, right? Numaflow is a Kubernetes native serverless platform for running scalable, reliable, event-driven application. It is possible through 3 pillars. First one is a Kubernetes native processing system. Very lightweight, very versatile, the same code can run on edge, on-prem, or on cloud. You will see, Sri will talk about some companies using Numaflow in production, and you will get a flavor of what we mean by is very versatile. Second, it is language agnostic, meaning you can write in Java, Python, Golang, and Rust. It's easy to add an USDK to it. We also have a couple of built-in sources and things, which is quite popular. But as you saw earlier, you can easily write a source and a sink. Lastly, scalability. We can auto scale from 0 to 1, many, and many to 0. This is quite important because these are fire and forget systems. We need to make sure that when there is no traffic, we should be able to auto scale the way it needs to reduce cost. And it is very, very capable of running on low resource footprint and on edge systems where there are no internet connections. With this, I'll give it back to Sri to give you a demo.
Awesome. Thanks, Vigith, for doing a quick introduction of what Numaflow is. But let's take a quick example and then try to understand what does it actually take you to write like a real-time event processing pipeline within Numaflow, right? So for this simple demo, probably I'm just picking up sentiment analysis because this is something that anyone and everyone can relate to. So on a very high level is what I'm trying to do is like we are receiving a bunch of events, and then you want to do a sentiment analysis on that event and then say that, hey, is it a positive sentiment or a negative sentiment? And then finally write the data to a sink. Now, let me quickly go to the next step and then see what does it actually mean? What does it actually take for you to write that in Numaflow, right? So within Numaflow, everything is like what we call is like a pipeline. So each pipeline is defined based on your vertices and edges. It's nothing but like a graph that you can build out, defining, hey, here are my vertices, and here is how the entire graph is built out. You can define all of your edges. We will show you the spec for even the sentiment analysis pipeline here. So first, you need a source where you're receiving a bunch of the events. This is your source vertex. And then the next is like you are doing a prediction saying that, hey, is this a positive sentiment or a negative sentiment? And then finally, you are writing the events, like the results, into a sink. Here, probably I'm just going to use in this pipeline like a log sink or whatever it may. That's something that is already available out of the box, but just for the demo purposes. Now, so as Vigith has mentioned earlier, like we have pretty much have a lot of inbuilt sources and sinks that are most often used by the community, and some of them have contributed back to the community as well. So as a developer or as a data engineer or as an ML engineer, if your sources and sinks are taken care for you, all you would focus on is just like this prediction, or maybe if it's some kind of an aggregation, the processing logic for aggregation, or some kind of event processing, whatever it may be, based on the use case that you'd have. as a developer or as an ML engineer or a data engineer, you'll just focus on this middle step, what we generally call as a user-defined function. Here, the example is like more of a prediction that we are doing on the event streams that we are receiving. So you just focus on this piece of code, which is here. And in this example, I'm just going to use a Hugging Face model that is already available that does the sentiment analysis for you. So let's try to see what does it actually take for you to write this small piece of code to start with, and then how do you build this pipeline spec, right? So moving on to the next slide, where you can see this piece of code, right? All as a developer you would focus on is just this data or trying to implement this function. This is a Python example that I have written. So it's a very simple where you are receiving the data, but here you don't know where you are receiving the data, right? Like you are not worried about your source because it's already taken care by the platform. It's not HTTP nor Kafka. There is no mention of any of your event sources as such. So you're just receiving some data that is provided by the platform to you, and then you're just acting on that data that you received. So you're just saying that, hey, what is the value? Doing sentiment analysis on that, and then just passing on that information to the next step. And then and when I say in this next step, we said that we are writing the data to some sink, but you don't know what sink it is, right? So even in this piece of code, you never mention like what sink or whatever. You are just saying that, hey, I receive the data, I process the data, and then I just send it to the next step. And when it comes to the processing, though, here is just like doing simple sentiment analysis. There are a lot of complex things that you can actually do with the data. It can be some map functions or reduce aggregations, anything that you would want to get that you generally have with any kind of like real-time stream processing systems like a Flink or any of those. You have all of the streaming semantics available into the platform in any language that you like. So I'm just showing you a Python example here. And then what does the pipeline spec look like here, right? If you take a look at it, we said that you need a source. If you look at this, it's a pipeline. It's a custom CRD that we have implemented for Numaflow, where you have the pipeline as a kind, and then you define your spec saying that here are my vertices where I have a source, I'm doing an inference or the prediction in the middle step, and then finally writing the results to a log sync, which is already baked into the platform. It's an out of the box sync that is available for you to debug and all of that. And then you're defining how are the edges defined. So first I'm from in to sentiment inference to log is how the pipeline spec is the edges. That is what I've shown in the earlier diagram is what it's going to look like. So in short, as a developer or as anyone who is interested in doing processing, you just focus on this piece of code, and the sources and sinks majority of the time are taken care for you. But if you have custom use cases, you can implement your own source and sink. And then the inference part of this processing logic is just nothing but a container here. So it's as simple as that for you to create any kind of like event processing pipeline in Numaflow, not worrying about the operations and auto scaling and all of that. Let's try to see, like we mentioned about auto scaling and all of that, right? I'll show you multiple pipelines that we are running like in production at Intuit, and then see the scale at which we operate and also the different languages that we are actually using and all of that. So let's start with a very simple example, and then I'll try to take you to like very complex pipelines as well. So the first one I mentioned about is like the sentiment analysis pipeline, right? Let's say this is here is the UI. All of this is available as part of the open source project. It's not a custom UI that we have internally only for Intuit or anything. It's part of the open source platform. You get all of the bells and whistles, right, from that help you to debug very close to where you are trying to build your pipelines and all of that. So let's take this example, right? Like where I have my HTTP source. Just I'm sending a bunch of events to this HTTP source, doing a bit of inference on the data and writing the results to the logs. So I'm not sending any of these events right now as I'm going through the demo, but I'll show you the other pipelines where we are processing like thousands of events in real time. So if you take a quick look at it, each of these are what I said as like vertices, and these are your edges. And you can, if you want to understand what is happening with the health of the different vertices, you can take a look at all of those metrics here within the platform itself. You can take a look at your logs and all of that. How much memory are you consuming and all of those. And you can because if you are writing into a log, you have a log sync here, you can see the results and all of that within the platform here itself. Let's say, for example, I've sent some events earlier. You would see some of those results in the logs here, but I think it's scrolled through. But let's take a different example and then try to see how complex can your pipelines get. So let me take another one. This is like a real production pipeline that we are running at scale. Here, I'll also touch upon the multi-language support that we mentioned, auto scaling and all of that. So if you take a look at it, we are reading the data, and this particular pipeline is used for our observability needs, where we do real-time aggregations of like availability and various other metrics that are important for our to meet our SLAs and monitoring needs and all of that. So our input is basically a Kafka where we receive all of our events. And if you look at it within our call itself, you'll see the number of events that we are processing can range from like 5,000 events per second to 10,000 events per second to very small. So these events come in like a particular set of bursts, and then you try to process them and then to take it forward. So this is your input source. This is what we are using as like Kafka. We have like inbuilt Kafka source that you can actually use. And then after that, once you receive those events, we are doing a bit of pre-aggregation. So you can think of this pre-aggregation as most likely like a lot of map reduce kind of aggregations that you would want to do. And similarly, after you do pre-aggregation, you do post-aggregation, and then you're actually sending the events to multiple, like once you process that, we are sending to multiple things. One of them, we are sending it to Kafka, and then we are doing some kind of anomaly detection on that data. You'll also see that next pipeline, like all of that. And we are also sending the same set of data to one of our observability tools called as like Wavefront, where we are storing all of these metrics. We use it for dashboarding needs, alerting, and all of that. So all of these events are processing the data. All of these pipelines are processing the data real time, and then like aggregating the data and all of that. So the another thing that I want to really touch upon here is like the auto scaling piece, right? When we looked at those earlier challenges, we mentioned about the complexity of doing event processing or the real time stream processing. The second is like auto scaling, the platform challenge, auto scaling challenges, and all of those, right? But if you look at all of this entire pipeline in itself, each step has its own dedicated set of pods. It's like you have like 3 pods running for this particular input vertex, and then you have like 5 pods running for pre-aggregation, 3 for post-aggregation, 5 for like publishing to a sink, and 1 only just to Kafka. And each of these, if you look at it, we have during our conversation itself, we saw it was at like 500 events per second to 100 events per second, and now we are seeing a burst of like 2,000 events per second, right? We scale each of these individuals vertices based on multiple factors. Like one is we understand what is the backlog that is there upstream from your event sources, and at what rate can you process, and then also what is your downstream dependency. Let's say you are writing to a DB, and probably there are only so many connections that you can have to DB. So you're always throttled, right? You cannot scale your steps that are before. You can only scale your steps before that to an extent, not beyond a particular point. So we understand all of these semantics, like what based on the back pressure and all of that, and then try to scale each of those components, what is only required, and make sure that we process the events at the scale that is needed. So see again, like you can see that the number of events dropped from like 2,000 to like 500. So we always keep on seeing that in cycles, and then based on the requirements and the need, these pods or the scale such that you don't have any like latency issues or any of those. So that's and the third thing that I want to highlight upon here is this is a polyglot pipeline. We said that you can use any language that you would want to write. So for example, some of our pre-aggregation steps are written in Java, and then post-aggregation, some of the team is written in Go. The reason is that because like when you think about your teams as such, some of them could be really experts in like Java, Python, or even Go. So you can use any language that you'd want to use, and then you can come together and then build out these pipelines and use your own processing logic, whatever you would want to do, because each of these are like individual containers themselves, and then you can just package your logic into that, and we take care of the auto scaling, sending data movement, and all of that. So end to end. So that's like one pipeline that you can see right now. We are at like 4,300 odd events. This is like a real-time pipeline that you are seeing in action, where we are processing the data for all of our observability needs at Intuit. Now let's move on to another example, like which is even more complex, the complex structure and the complex pipelines that you can actually build with a platform, and even it has a bit of flavor of like ML into it. So this is our real-time anomaly detection pipeline, where once we process the data in the previous pipeline, we try to do anomaly detection to say and understand that, hey, whatever we are seeing in terms of these metrics, are they anomalous behaviors? If they are anomalous behaviors, probably we need to send out alerts to the team so that they can start debugging and like whatnot, right? So once we receive all of that data, we are doing a bit of pre-processing here, and then we are sending it to inference. Inference is nothing but a prediction where we are doing an anomaly detection saying that, hey, is this anomalous or is not anomalous? And then we are doing a lot of pre-processing and then writing it to multiple sinks. But in short, if you take a look at this pipeline, it has all the features like whatever we have mentioned about, either right from like reading from one source, doing conditional forwarding to multiple places, using multiple languages. This is, let's say, for example, inference is written in Python. We also use the same pipeline to trigger some of our training workflows related to the anomaly detection models. And pre-processing is actually in Java. So using as we mentioned earlier, like one platform that solves for like connecting to multiple sources and sinks. uh, Use any language that you're interested in to doing any kind of event processing. And then also the platform takes care of auto scaling. Like you can see it here, each of these individual vertices, they are at different, like you have one pod here, two pods here, four pods at the source, three at inference. So we understand the end-to-end pipeline at what each step is processing, and then scale each of those steps individually such that you don't have any kind of like consumer lag and all of those in short. And lastly, as a platform engineer or any developer, you'd be more interested in also debugging any if you have any issues, right? Like as I showed earlier, you can quickly take a look at all of your logs here in itself, and then look at understand your metrics, whatever is most important for you. We provide all of that close to the platform so that it's like one end-to-end platform, right from like processing, operations, and maintenance, and doing any kind of debugging close to you, wherever you are. So that's the power of the entire Numaflow platform as such. And these are some of the examples that we are running at scale at Intuit. And there are a lot more within the community I'm going to share in the next upcoming slides. So let's go there. So here are some of the other use cases. Like we have just quickly sampled out some of those so that we can show the breadth of the use cases and the various places where like Numaflow as a platform is being used, right, for real-time event processing use cases. So as I said, it's like from fintech to aerospace, you can see across the board where teams are using it for, like, first, as I showed one of the pipeline at Intuit, we are using it for anomaly detection, like various hundreds other use cases. And the second is like, Lockheed Martin uses it for like IoT data processing. And then B Cubed is basically they are into doing event processing of radio frequency signals on like edge devices. So when we think of edge devices, you are constrained with resources and all of that. So Numaflow as a platform, or some of these pipelines are so lightweight that they were able to write the processing logic that they were interested in using Python, and then just deploy it in very small devices so that they can do some radio frequency signal processing and all of that. And Atlan, they are a very good startup, and they are more interested. They're focusing on like real-time notification systems and data movement and things like that for their internal use cases. And Seeker uses it for like some of their ML pipelines. And then Valiga Chain, they use it for like kind of like a fraud detection on blockchain data. So if you look at all of these breadth of use cases, right, right from like fintech to aerospace to like some kind of industrial teams, they are using Numaflow for doing event processing. And from it could be like very few events to any scale that they would like. That's one part. And the second is using the languages that they are interested, connecting to any sources and things that they would like. So in short, like some of the pain points that I've mentioned are not just for Intuit. They are something that are really resonating with like the community across the board. And these are some of the pain points, like as you would be coming across if you are trying to build any kind of like event processing systems or real-time stream processing systems. Uh, you should absolutely take a look at Numaflow. And moving on to the last slide. So if you have really liked whatever we have shared today, so you can learn more about Numaflow by just quickly scanning the QR code, or just search for Numaflow on Google. You should be able to find our GitHub repository. So do star us if you absolutely like appreciates the support, whatever the team is trying to do and as a platform and trying to open source to the community. And at the same time, you can get updates and all of that. So we have a link to the Slack channel on that. You can on the GitHub repo, I can show it that quickly to you. But if anyone is interested, we are completely an open source project. Absolutely, you can look at the issues that we have, good first issues, or anything that you are interested in. Like feel free to pick them up and then reach out to us. We'd be more than happy to help you. And if you want to you have learned about Numaflow, where multiple teams, multiple companies are actually using it for different set of use cases. If that is something that you kind of resonate with, absolutely try it out. Reach out to one of us or join our Slack channel, and then share any comments or any thoughts or any use cases that you might have that we could possibly support or you would want to contribute. Yeah, we'd be more than happy to have you as part of our community. Let me quickly show you that GitHub repo. You can just go to Numaflow. You can see all the various set of use cases, like quick introduction, like the various use cases and all of that. You can look at our upcoming roadmap, and also you can join the Slack channel right from here. And do star us if you really liked our conversation today. Yes, and also we'd be presenting at KubeCon. Like Paul mentioned earlier, we are doing multiple talks at KubeCon, different set of use cases, right from like ML use cases to real-time event processing use cases. And also we are going to share about how our payroll platform team is trying to reimagine their entire architecture using event-driven approach, and how they are actually using Numaflow to solve some of their pain points. You have like multiple talks. We are going to talk about all of these, and we have one which is like through the on the DoK day itself. So Vigith and another colleague of ours is going to provide a talk on that. But yeah, that's pretty much it for today, where we wanted to share about some of the pain points of like real-time stream processing or event processing, and how did we go about tackling them with Numaflow. Yeah, we are open to take any questions, any thoughts. Yeah.
All right, thanks so much, Sri and Vijith. Yeah, we do have one question right now from Jakob Scholz, who said, how would you compare Numaflow to something like Flink, for example? What would be the advantages, disadvantages?
We use Flink heavily at Intuit. It's mostly as a data processing framework, right? To do very high throughput data processing. The way you look Numaflow is more on a eventing side. For example, users can write code in the procedural way they know rather than to learn new semantics. So if you are familiar with Flink to do data processing, Flink is the way to go, right? But what we found out, most of the developers are not data engineers, like they're application developers, and they want single image. For example, think about in Intuit ecosystem, right? We use Argo CD to deploy applications. We wrote Argo, right? And they want the eventing system to be along with the same Argo application. The eventing should use the same container image that is being written, because there's a lot of code that is being shared between the HTTP endpoints and the eventing framework. If you are doing so, just to reiterate, if you're doing data processing, right, and if you are very familiar with Flink is quite good to use. I wouldn't compare like A versus B, rather it's more of a choice based on the constraints you have at hand.
Just adding to what Vijit has mentioned, right? Like one of the things that has been really resonating with the community is when we think of like the likes of Flink, it's primarily like a huge Java shop that you would have to get into. That's one. And the second is you'll have to learn a lot of like these real-time stream processing concepts. But if you take those examples of like, let's say B Cubed or any of those teams, they want to do real-time stream processing, but they're not really well versed with like Java, or probably moving into a new platform that is bulky for them to manage and all of that, like Flink. So That is the most important piece that is really resonating with the users, even internally or externally, is like, okay, I can just use my own language, which I'm really comfortable with, but I still get all of the streaming semantics, like doing any kind of aggregations, reduce map, whatever is needed, that is available through the platform. So we are just getting closer to anyone wherever they are, rather than making them move away from their existing ecosystem to a new platform altogether as such. So that's the biggest value prop Numaflow as a platform provides you to anyone who is interested in like stream processing or any of those. Yeah.
Okay, cool. Thanks. Actually, I have a question as well. That's from me. So, what monitoring and observability features does Numaflow offer?
Oh, so I think that's a very good question, because this is something pretty much all of our developers keep on asking us. So like, as I showed you in some of these pipelines, right? Like the first is we ensure we emit metrics that will help you to monitor in multiple folds, either in terms of understanding what is the health of the pipeline to start with. You can see that we publish some of those metrics and the components that we use internally. We publish saying that are they healthy, are they running, and all of that out of the box. That's one. And the second is we publish a lot of metrics so that you can understand the end-to-end latency of a pipeline and all of those. You can also uh, yeah. You can also I'll show you some of the debugging features within the platform itself. So these are like various metrics that we publish out of the box for you. You can create any kind of alerts on top of these, and so that you can monitor whatever you are interested. You can find this in the documentation itself, like anything that you would want to look from an operator manual perspective. The other thing is like the logs and all of those, which the users, let's say, for example, you want to quickly debug, probably you might be ideally going to Splunk and looking at all of those. But if you want to quickly look at what is happening, we have all of the logs and everything available close to your pipeline itself, so that you can just quickly take a quick glance and then try to debug from there itself if need be. So all of these are part of the like nice UI close to you wherever you are. And then we publish the metrics, whatever is most important. Yeah.
Okay, thanks. And then we have another question from Robbie. So, he's asking, so does Numaflow require Kubernetes?
Yes, we are a Kubernetes native platform, and it is built for Kubernetes for event processing.
Okay, great. Are there any other questions? We'll wait just a second because there's a little bit of a delay between us and the stream. So we'll wait a few more seconds here. But if there are no more questions, we'll move into the quiz, which will, and you can win a free Data on Kubernetes shirt. Actually, you both can participate as well, because the questions are not based on your talk. Well, it seems like we don't have any other questions yet, but thank you so much for the presentations. It was really informative, and I think, yeah, a lot of people could get a lot of use out of Numaflow. So, yeah, thanks for spreading the word. I think we'll start the quiz. So that'll take a second. You get out your smartphone, there will be a QR code that you can scan. Let me get that popped up here. There we go. Here, okay, so if you scan this QR code, we'll do a little quiz. It's just some pretty simple questions, mostly based on the introduction here. So if you scan that, you can get in on the quiz. Just 4 pretty simple questions, and the faster you answer, the better. The more points you get. So if people answer the same questions, and give the same answer, the correct answer, it's whoever did it fastest. So, yeah, if you participate and you win, you will get a free Data on Kubernetes shirt. Don't be shy. Scan the QR. Okay, we've got at least one. I can't participate because I know all the answers. I created the quiz. All right, we're getting started here. All right, we've got some players here, 6 players. All right. Question number 1. In which city will the next KubeCon EU take place? Okay, we've got Madrid, London, Utrecht, or Brussels. Fast answers. We'll get you more points. All right. London it is. April 1st through 4th. CFP is maybe I shouldn't Maybe I gave you the answers to some future questions. Well, we'll see. All right, Android in the lead. Question 2 of 4. Okay, here we go. When does the CFP for KubeCon EU close? October 31st, November 24th, December 25th, or January 1st? All right. Looks like most of you got that one right. Nice. November 24th. That's the date. So if you're thinking about submitting for the EU conference, you better get working on your submissions now. Now that, just to be clear, that's for KubeCon and not for DoK Day. That will be a separate CFP. Okay, 2 more questions here. Will you be the winner? Okay, which CNCF project and recent DoK talk guest joined the DoK Community Collaborator Program? All right, is it Vitesse? Is it Kubeflow, Longhorn, or Strimzy? Ooh, all right. Well, a couple of you got it. It is Vitesse. So they joined us. We had a talk from Deepti Sigaretti last week, which was a great talk. So we welcome them to the Community Collaborator Program. All right. Okay, Android, still in the lead. See if you can hold together for this last question. Okay. What are the 2 strategies mentioned for running fault-tolerant and cost-optimized Spark clusters in EKS? Data replication and load balancing. Oh, I can't. I'm just going to let you read all those. Okay, well, that one was a tough question. Okay. I think our leader is Android. So, Anne, I don't know who you are because it's anonymized, but you can reach out to me on LinkedIn, on the DoK Slack. Just let me know. You can I'm Paul Au on LinkedIn. AU is my last name, or Slack. Reach out to me and give me your address and your shirt size, and we'll send you a Data on Kubernetes shirt. Again, I want to thank Sri and Vigith for today for presenting. Yeah, hopefully we'll see you at DoK Day or at KubeCon.
Okay. Thanks a lot.
Yeah, thanks. All right. Thanks for coming.